Hello everyone. So in the last video we started talking about partial ordering, and so basically partial ordering is all about having, well, before having any of these, it's so the equivalence relation is sufficed when you have these three properties sufficed in a given set. So you have reflexive, symmetric, and transitive. Now, when it comes to partial ordering, there is a property that has to be done differently, which is, so we have symmetric, antisymmetric, and asymmetric. Symmetric is when you have A are related to B and B are related to A, so you can go both ways. But asymmetric is asymmetric drops this relation in the sense that A are related to B is not the same as B are related to A. And then you have something in between, which is antisymmetric. Antisymmetric is when you have A are related to B and B are related to A, and these are equal to each other only when, this A are related to B and B are related to A is only sufficed only when A equals to B, and this is the antisymmetric, and this is what is called partial order. And through partial order you could use what is called the hash diagram, and the hash diagram eliminates all these paths and lines up the dots from bottom to top, and then you have the lower bound and upper bound, and then the the complete order, I think, the proper, I can't remember, partial order, and then you have the total order when you have all these lines. There is no branches to the side, and this is called total order. So that is what we studied the last time. So in this video we are going to keep going with the slope. We've talked about the slope being a primary, the slope being y equals m of x, and I think we should define a new page here. Just create a new page. So then we go like slope, and then we should define the necessary information within. So let's copy the necessary information from here and move them to the symmetric, and then this is the slope stuff. So move it to the slope here. There we are. M being the magnitude of the slope, the sign of m determines the direction of the slope. The smaller the m, the smaller the slope. The bigger m, the steeper the slope. The slope basically is almost impossible for it to be vertical. It has to be infinitely large, which is not really a number. There's something else we should consider, and that is the when we started talking about binary relations, the change in y and the change in x. Okay, anyways, so let's keep going with the slope. So today's topic is we talked about single point slope, a single point form slope, and then we have another, which is, alright, let me open up YouTube videos. So the last time we talked about the slope, which is so let me quickly skim through this.
In the last lecture, we saw the amount of change in the line's elevation amount in the same distance is negative 2. The elevation of a horizontal line doesn't change regardless of 2 units. The slope of this line is 2. But let's say we want is equal to c, Delta y divided by delta x is the same as c times the slope divided by c,
I think I've copied.
or simply the slope.
I think I've copied this information, but let me try to look it up. So this is the summary of the information we had the last time. So I'll just copy it to the Notion and pick up the pace from there. So that's that. So to quickly recap on a linear function passed by the origin, y equals mx, affine functions, linear functions, and a constant, which basically moves the slope by some constant. There's a line does not pass by the origin, so the line does not pass by. So this is a linear function. An affine function is when you have the slope passing by a different intercept, so a certain y-intercept. So you can have this line passing through here. So it passed through the y constant, that is. Basically, it moves a certain distance away from the origin by c constant. Also, x plus or minus c, so it's either in the positive or the negative direction. This form is called cold slope intercept form. The c is the constant, which is called the translation unit. Y-intercept is the point where the intersection happens on y-axis. That's the y-intercept. The y-intercept is the point where the intersection happens on the y-axis. Okay. In order to calculate the slope, we take any 2 points on the line. Example, we have 3, 3 or 4, 4. Notice it is 1 unit apart on the x-axis. Taking the y-coordinate values, we get 4 and 3. Yeah, so slope, we take any 2 points on the line. So you get these 2 points here, 4, 4, and some point here. I'm not sure what the point is. So it's just an example anyway, so it has nothing to do with the graph. It's 1 unit apart. Yeah, 3 and 4, it's 1 unit apart. In this case, it's basically 2 units apart on the x-axis, and like 1, 3, 6, 7 units apart on the y-axis. Taking the y-coordinate values, we get 4 and 3. Subtracting those leads to 1, and that is the slope. It's denoted by the symbol delta. So delta y, if the change in x is not by 1 unit. We usually calculate for 1 unit to get the slope and multiply by the change in x. If x changes by 2, then the slope would be slope by 2. 2 being the change in x. Okay. So the 3 is delta x and delta y. Assuming delta x is c. So delta y equals c multiplied by the slope. C's cancel each other, making the slope being the change in y over the change of x. Delta y is called the rise, and delta x is called the run. So you got the rise, that's the delta y, and then the run this way is called delta x. So that's the deal with slope. That's what this video is about.
This equality tells us physics as well as in other branches of science and engineering. If we know the coordinates of any 2 distinct points on a line, we can use delta y over delta x to calculate the line's slope. As an example, let's use this to calculate the slope for a line which runs through 2 points with coordinates 3, 3 and 7, 7. As a second example, let's calculate the slope for a line which runs 4. Let's say in 4, 3. Delta y is the y-coordinate of the right point minus the y-coordinate of the left point, which is 5 minus 3, different pair of points, 4, 3, and -6, -2. Once again, delta y is the y-coordinate of the right point minus the y-coordinate of the left point, or 3 minus negative 2, which is the same as 3 plus 2, or 5. And delta x is the x-coordinate of the right point minus the x-coordinate of the left point, or 4 minus negative 6, which is the same as 4 plus 6, or 10. So the slope delta y over delta x is 5 divided by 10,
1 over 2.
or 1/2. The same delta y over delta x value is the slope of the line. The line we choose, the calculation for slope will always result in the same value. This makes sense since, as we saw, the equation for a line contains a single constant m whose value is the slope of the line. Since there is only one value for a line slope, a line must have the same slope everywhere, no matter which 2 points are used in the calculation. As a general example, let's call the left point point 1 and the right point point 2. We will refer to the coordinates of point 1 as x1 and y2 minus y1. This is the general phase referred to as the rise. In the next lecture, we will use this formula for slope to create a different form of the equation for a line called the point-slope form.
Point-slope form. Let's see what this is all about.
And we'll form y equals mx plus b. This form of the equation of a line is called the slope-intercept form. The slope-intercept
So the slope-intercept form is basically when you have, let's start an notepad.
form involves two constants, m and b.
Okay. You have y equals mx plus b. M and x being, oops. Yeah, m and b being constant. M is the slope here, and b is the transition.
The numerical value of m is the slope of the line, and the value of b determines the point at which the line crosses the y-axis, called the y-intercept. The y-intercept is a point on the y-axis with coordinates 0, b. The slope-intercept form has the advantage of being simple, but is only useful when we know the exact point where the line crosses the y-axis. In some cases, when looking at the graph of a line, it may be impossible to determine the exact coordinates of the point where the line and the y-axis meet. However, we are often able to discover the coordinates of some other point on the line. There is another form of the equation for a line which we can use in this situation, called the point-slope form. Using the point-slope form, in addition to the line's slope, we only need to know the coordinates of one point somewhere on the line. The point-slope form of the equation for a line can be derived by using the formula for slope which we learned in the previous chapter. You may recall that this formula uses the coordinates of any 2 points on a line to calculate the line's slope. If we call the coordinates of these 2 points x1, y1, and x2, y2, then the slope is the difference in the point's vertical positions y2 minus y1 divided by the difference in horizontal positions x2 minus x1. Now, let's say we have a line with a slope m and a point on that line with coordinates x1 and y1. If we use any other point on the line as the second point in the slope formula, the calculated slope will always be equal to m. On the other hand, if we use a point which does not lie on the line, the calculated slope will not be equal to m. So only points which lie on the line will produce the correct values for m, and thus satisfy this formula. This line can therefore be thought of as a collection of all points with coordinates x and y which satisfy this equation. This equation is easier to read if we rearrange it so that the y's are on the left side and the x's are on the right. To do this, we multiply both sides of the equation by x minus x1. This allows us to cancel the denominator x minus x1 on the left side of the equation. The result is the point-slope form of the equation for a line. Let's try an example using this form to write the equation for a specific line.
I should check on how to write the LaTeX form in Markdown format. Let's keep going.
Let's say that we are given the graph of a line, but not its equation. We are told that the line has a slope of 3/5. Since we know the slope, we might try using the slope-intercept form to write the equation for this graph. We start by assigning the value of the slope, 3/5, to the constant m. But from looking at this graph, the exact point where the line crosses the y-axis is not obvious, so we don't have an exact value to assign to the constant b. But let's say that we know that the line passes through the point 4, 3. Since we know the slope and the coordinates of one point, we can write the equation for this line using the point-slope form. Since the slope is 3/5, we assign a value of 3/5 to the constant m. And since the coordinates of the known point are 4, 3, we set the value of x1 and y1 to 4 and 3. So the equation for this line in point-slope form is y minus 3 equals 3/5 times the quantity x minus 4. You may sometimes see the point-slope equation written with the variable y alone on the left side. To write the point-slope equation in this form, we simply add y1 to both sides, canceling out the negative y1 on the left, which gives us the point-slope form with y alone on the left side. Now let's try another example using this form. Once again, we are given the graph of a line but not its equation. And once again, it is not clear from looking at the graph exactly where the line crosses the y-axis. We are told that the line passes through the point -7, 3, and that the line's slope is -2/3. Using the point-slope form, we set the value of m to the slope, -2/3, and the value of x1 and y1 to the coordinates of the known point, -7 and 3. This equation can be simplified if instead of subtracting -7, we add +7. The equation for this line is now written in point-slope form. Since we now have an equation which describes this line, we can determine the graph's y-intercept. It is difficult to tell by looking at the graph exactly where the line intersects the y-axis. However, we do know that the x-coordinate of this point must be 0, since every point on the y-axis has an x-coordinate of 0. Therefore, if we set the value of x in our equation to 0, we can solve the equation to find the corresponding value of y for that point. Completing the arithmetic, we add 0 plus 7 to get 7, and multiply negative 2/3 times 7, which gives us negative 14/3. We can then write 3 as 9/3, and add negative 14/3 to 9/3 to get negative 5/3. So the point on the graph with an x-coordinate of 0 must have a y-coordinate of negative 5/3. The y-intercept is therefore 0, negative 5/3. Since we know the y-intercept, if we like, we can now write the equation for this line in slope-intercept form. We already know that the slope is negative 2/3, so we assign this value to the constant m. And since the y-intercept is 0, negative 5/3, we set the value of b to negative 5/3. So the equation for this line, written in slope-intercept form, is y equals negative 2/3 x minus 5/3.
Minus 5/3 with that given us.
Both of these forms are equivalent ways to write the equation for the same line. We can prove this by converting the top equation to the bottom equation's form. We do this by distributing negative 2/3 to the two terms inside the parentheses. Instead of adding negative 2/3, we can simply subtract 2/3. We then eliminate the parentheses and multiply negative 2/3. We can then write 3/3 to get negative 5/3.
Denominator.
This makes the forms of these two equations identical. So, although the point slope and slope-intercept forms look different, once the proper constant values are assigned, the two equations express the same relation between x and y and are therefore equivalent. However, either form may be more convenient, depending upon the information we know about the line. In the next lecture, we will introduce an additional form of the equation for a line, known as the two-point form.
Right, so that's that for this video.